right. So, and today here the idea is that we're going to cover maybe, I think initially we had some discussions about how much things we can cover if we had some time to start with the topics on learnability, and then we decided it was a lot. So today we just compiled a few important concepts, or not what we think are important concepts, about some recurring themes in machine learning that come up a lot actually. So this way, like when we, and this is not an exhaustive list, of course, those are like some of the most important concepts that will come up. So for instance, when we talk about neural networks, we all know what a neural network is in like very simple word actually, or at least conceptually. And that's the goal here in this lecture today. Please, again, feel free to stop me anytime for questions. Okay, so again, we're not going to spend so much time on the motivation, right? I mean, we all know that those techniques are permeating every application or every possible field. Yeah. Right. And then the idea here is that the main challenge, I mean, the two main challenges are actually that people normally talk about in those aspects is it's actually the huge dimensionality. It's the huge dimensionality of the data, and the second problem is the size of the data set that you need for training. And those are the two problems when we talk about big data, and that's actually the only time that we'll use this today, at least, big data. But just to give a flavor, actually. And the idea is that basically learning in a very abstract sense allows you to extract a tractable data representation that you can later use, actually. This representation, you can use it for prediction, inference, you can use it for storage, you can use it for some other processing, any other operation. So from a philosophical point of view, maybe this is how we could view like as one umbrella where everything else fits. Okay, so we'll start off with supervised learning, right, which is also like one of the very common actually types of machine learning techniques that come up in the literature. And actually, here the idea is, again, everything is from a conceptual level. We're not going to be digging very deep into these, just like as a quick recap, actually, of these techniques, or introduction. And here, for instance, if you want to think about supervised learning, actually, it's characterized by the presence of a training set, right? And the idea is that you use the training set to build some sort of model that you can use for prediction, and then you test your prediction on a different test set from a very simple, high-level overview. That's how we can view them, actually. And then, for instance, the data model looks like that, right? So we have training data, right? And the training data consists, for instance, we can think about them as n input-output pairs, right? Where xi is the training, xi is a d-dimensional vector, and yi is scalar. And basically, xi and yi are pairs, actually, of input-output that you know. So you know that for this input, this is the output, basically. So this is the training set. And the idea, for instance, is you want to find a linear model, right? A linear, which is this W that we have here, that makes the pairs, right? Those pairs, xi, approximate the outputs, yi. And for instance, prediction in most of these aspects is a linear function. So you actually, the prediction for xi is W transpose xi. So it's very simple, actually. So this is in terms of like linear prediction. And actually, if you want to define how do these optimization problems look like? So what is commonly done is you define the loss function. And the loss function basically measures, I don't know whether you have, okay, sorry, yeah, that helps. Right, and here the idea is that this is your prediction, as we're saying, so you have xi, and then W transpose xi is your prediction, and now the target is yi, so this is in the training set. In your training set, you define this loss function, which measures those individual distances between what you're predicting, basically, and what you're and the actual value, predicted difference between predicted and actual, basically. And this is actually called and then you take a sample average. You sum them over all the data points, right? You sum them over I, and then take an average, basically. This is an empirical average. And this is actually in these contexts, this is called as empirical risk minimization, basically. And when you add a regularization parameter, then you call it a regularized empirical risk minimization. And regularization, actually, this prevents overfitting. Actually, we can talk about this actually in the next slide. We will allude to that. And this is actually, it turns out that this is a very generic problem formulation, because by picking different choices for the loss function, L, and the different functions for the regularization parameters, we end up with other very well-known techniques in supervised learning, actually. Or, so for instance, in this case, so if we plug in, if we let L be a quadratic loss, right? So it's just measure the difference, the square difference between yi and the prediction, the true value in the prediction. Then we end up with the famous linear regression, right? No, I think I should not move so much. Right. I don't know whether can you see me yet? Is it okay? Okay. I can move it. And here the idea is, for instance, if you plug in this squared loss, then we end up with this supervised learning, which is called the linear regression. And in this case, actually, your output is scalar. And just in very simple terms, a linear regression, I mean, it's just finding, you have a bunch of points, and then you want to find the line, the best line that fits them in a quadratic sense, in a quadratic error sense, actually. And for instance, here you can, if you set the regularization parameter to lambda times the 2 norm squared of w, then you end up with what is called the ridge regression. And actually, this one, this lambda w squared, acts as what they call an overfitting prevention mechanism. So basically, an overfitting actually, if we think about it in also very simple term, overfitting is actually when the number of variables in your model is much bigger than the number of data points in your system. So basically, your model becomes tuned, very tuned to the data itself, so that it performs very well in terms of training error, but it performs very poorly in terms of test error. So this is in a nutshell, actually. And basically, the idea here, for instance, is by increasing lambda, you penalize solutions where the weights are too high, actually. And this way, you provide low weights, actually, and this will also reduce your model complexity, and by that mechanism, also reduce the overfitting problem. That's one way to do it. Of course, there are many other ways. So for instance, you can also, with the same quadratic loss, with the same least square cost actually that we saw, now if you change the regularization parameter from an L2 norm to an L1 norm, you end up with this well-known lasso from statistics, which actually looks like that. And the idea here is that one norms, right? L1 norms promote sparsity. They give you sparse solutions. So by increasing lambda in this formulation, we could always, by increasing lambda, you're promoting fewer and fewer zeros in your solution in W. And then by doing that, you're reducing the model complexity and you're kind of mitigating the overfitting problem. But again, there's no way to pick those lambdas analytically. Actually, most often it's used by, I think the term is called cross-validation. So it's actually just empirical evaluation and you pick the best points. Okay, so please feel free to stop me if I'm going too slow, too fast. For instance, we can also think about another variant. So now when you change the loss function from an L2, from a squared norm, which was this, you change it to an L1 norm, which is an absolute value in the scalar sense. In this case, it becomes more robust because it's known that L2 norm is much more sensitive to outliers than L1 norm. So by doing this very simple formulation, you can end up with a specific optimization problem where you have an L1 loss and an L1 also regularization parameter. And this is also called the robust regression. And again, lambda, you can increase lambda to control overfitting in the same way that we talked about in the last case, in the previous. So as you can see, like everything is kind of special cases of this original problem. We can actually think about one more instance of this problem that we talked about. And actually here, for instance, by changing the loss function to this weird looking equation actually. Sorry, yeah?
Can you emphasize more on the previous slide that
yeah.
Why the L1 norm is increasing this the sensitivity to outliers?
Right, because I mean, if you think about it, the L2 norm, this is my interpretation actually. So this is a square norm, right? And this is a 1 norm. So anything, if you have an outlier is a large deviation between prediction and true. And if you square that norm, it's bigger than if you take that norm itself, actually, that absolute value. Right? Is that...
No, I mean, yeah,
that's my intuition, actually. Yeah. But again, this is not a lecture, right? So this is a meeting. So if anybody has any better interpretation, that's the point where we jump in, actually. But at least this was my interpretation. Okay? Right. So now actually we can, again, if we go back to the original problem formulation and we replace this particular loss function, which was by this weird looking equation. We don't have to worry about this one actually. Now and then, if you constrain your outputs yi, so the target value, if you constrain them to be binary, then we end up with those well-known famous support vector machines or SVMs. And this is basically a binary classification problem, right? You have a bunch of unlabeled data, and then you want to classify them into one of two categories, right? Something that is such that what we have here actually. And here the idea is that this loss function, if you want to get an intuition actually of this particular loss function, the idea here is that when we look at, actually sorry, I just noticed that there's a typo in those slides actually. So actually this should be xi, and here as well. This should be xi. I'll correct them and update the slides actually, I just noticed. So actually if you look at this specific loss function, so for instance here, what is the idea behind the specific loss function? So for instance, so if, no, I cannot move so much. Can I move the flash? Let's see, yeah. So for instance, if we try to look at this specific instance, right? So for instance, if W transpose X, the prediction is 1, and the true value is 1, then 1 minus 1 is 0, so then the loss is 0. You're not penalizing correct decision, and basically you only penalize incorrect decision. For instance, just to get an intuition. Right, and this is how the optimization problem looks like. Yeah. So as you can see, there's a lot of different flavors. Yeah. So there's lots of different flavors that fit under this particular problem formulation. So basically, I mean, this is I think enough to give us enough. I mean, this is enough suggestions to give us an idea that learning can be seen as an optimization problem, or has a lot to do with optimization problem. So for instance, exactly in this genetic formulation that actually we can call, actually I'm just going to refer to as f of w from now on. So f of w is the loss plus the regularizer actually. So the whole thing that we're going to call f of w. And the idea is that traditionally this is in general solved actually by very low complexity algorithms. So for instance, doing like, for instance like doing matrix inversion, that's out of the question. So basically, the idea, the runtime complexity of most of those algorithms apparently is around, is linear in d times n, is O of d times n, where actually d is the dimensions of the data, the dimensionality of those vectors, xi's, and n is the number of data points in your training set. And that's the problem, right? Because it scales with if you have high dimensions of the data, that's bad, because it scales with that as well. And if you have a huge number, or if you have a huge number of data points, that also scales. So basically, that's the problem with those conventional algorithms. So the idea is that they need to do better than that. This is still bad news, actually. And now, actually, I'll just give a few slides on just a summary of what kind of methods they're using, actually, and what are the challenges with them. Okay, so for instance, we'll start off with the first, with probably the simplest case, which is L, and the problem is that it's actually the problem with smoothness, because a lot of those loss functions are not smooth. A lot of those regularizations are not smooth. And here we can probably just mention a few different cases, actually. The simplest case is, of course, when when L and R, so the loss and the regularization, are both smooth. So basically F is smooth, right? F is the sum of the two. So if F is smooth, then the gradient is defined, actually, and in most of these cases, most people do gradient descent, which is really simple, actually. Or steepest descent, basically. You just move along the direction of the gradient, which is the direction along which the function decreases the most, and then you just like go with a specific step size, basically. It's an iterative method, obviously, and the complexity is O time is actually scales with D times N, and that's still bad news, as we were saying before, because this is still a lot, actually. So if either the dimension increases, the dimensionality increases, or the number of training points increases, then this will blow up, actually. So that's still bad news, despite its simplicity.
Do you mean to approximate solution?
Sorry?
Do you mean to approximate solution? Complexity, or
the complexity
because
of...
I guess you will converge to a true solution. It should be to some epsilon solution.
Sorry, I'm not hearing well, actually. Can you raise the voice?
So I'm wondering, like, this is the complexity to find an approximate solution. Or
exactly, of course. Exactly. Within a tolerance of the true optimum solution.
Okay.
Within a tolerance epsilon of the true optimum solution. Absolutely. Yeah. Right. Exactly. So as we're saying, like even this very simple scheme is still problematic in terms of complexity. So for instance, we can think about, there are many other cases, for instance, where F, you can write F as a sum of a smooth part and a non-smooth part, actually. And there are lots of cases, or lots of those previous techniques that we talked about that can be covered under this, actually. And don't worry, this is just a, here we're just giving a very simple overview of those methods. So when we talk about proximal points, we know what we're talking about. And then we're going to actually dedicate some more time to that, actually. So these techniques will come up later. This is just an introduction so that when we talk about proximal points, that, I mean, we're all under the same page, on the same page. Right, so for instance, we can think, as we're saying, like we can think about many cases where F is a sum of a smooth plus non-smooth part. And in these cases, actually, the gradient for the non-smooth part, for instance, is undefined. And that's the problem. So the gradient of F doesn't work anymore. So for instance, one type of methods, or one class of methods actually, because there have been many variants on this one, is this, it's known under proximal point algorithms basically. And without having to look a lot into the details, actually, it's kind of a combination of gradient. You take a gradient, it has a flavor of a gradient, right? Plus what is known as the proximal operator, which we don't have to worry about that now. We'll probably cover that at in some other lecture, or in some other meeting, or in some other papers. And the idea here is that also it's another iterative method. And the idea here is that complexity-wise, it's still very similar to the gradient, and it's still actually relatively high as far as these techniques are concerned, actually. Right, so again, another possible case we can think of, it's actually when both L, so for instance, when L is non-smooth, but R is smooth, for instance. And in this case, we can, the gradient actually still doesn't exist, but we can think about some other generalizations, actually, or some other cases where people have used the subgradient, actually. And actually, in a very simple way, the subgradient is a generalization of the gradient, actually. So, so actually, the subgradient is equal, becomes the gradient when the function is smooth. So in that sense, it's something that is more abstract and more generic, and more applicable, of course, than the gradient. And actually, people have developed also subgradient methods, which are exactly the equivalent of the gradient method, but except that instead of moving along the gradient, you move along the subgradient. And here as well, this is just a very simple, just to provide a very brief overview. We're going to be covering that at some point, I think, in the future. Okay, so as we've said, like the problem is that the complexity for these techniques is still too high, actually. So as far as large data sets are concerned, or like if you have high dimension data, then that's still a problem. So for instance, like to get a flavor of what has been done to mitigate that. So for instance, like if we can actually rewrite the function, so this loss, this empirical loss, as a sum of the individual losses, where Fi is the ith loss, so basically corresponding to sample I in your training set. Let me move this way. Right, so and then in this case, right, so your gradient becomes a sum of individual gradients for all the points in your, for each data point in your system. And as we're saying here, n is the number of points in your data set, and n is basically very large. So to get the gradient, basically, you need to add up the contribution of all those points, right? And that's the limitation. That's why it scales with the number of points, actually. So all gradient-based methods. So that's the problem. And actually, and that's the reason it's too expensive. And here people have came up with some clever alternatives, actually. They were actually, I mean, the main motivation was not that, but people have figured out that this is a very good fit for data, for like those large-scale learning problems. And this is actually the stochastic gradient descent. And again, we're going to be devoting a lot of time, I think, to that at some point later. This is like widespread in neural networks training, deep learning. I think this is the basis of backpropagation as well. And here the idea is very simple, actually. So instead of like getting the full gradient information, you pick you pick a random index from all the set of indices in your system. You pick actually, or maybe you can put it in another way. You just pick the index of a random point, and then you compute the gradient for that, and you go along the gradient for that point only. And then under some conditions, actually, this will converge. And we're not gonna dig deep now, but just to give everyone a flavor of what is the motivation. So the idea here is complexity, saving complexity. Right, as we're saying, so here basically you can see that as updating the elements of W in like one component at a time. So you have a vector, and then you actually update one component at each iteration. And under some statistical assumptions, that will converge actually. That will have the same effect as like the gradients, but at lower complexity. And here the great thing is that the complexity just is linear with the number, with the size of the vector, the dimension of the vector, D. And that's actually why they are so attractive, and that's why they are very popular. They're like getting increasingly finding applications in most of those optimization problems. They could also actually be extended, they have been extended to cases where the function itself is non-smooth. So basically, there's such a thing as subgradient methods.
Each time if you just select one, because that means that it takes more iteration steps.
Not necessarily, not necessarily. Yeah, and I mean, in theory, no. In theory, no. Because, I mean, convergence-wise, it's going to be the same, actually. But in terms of, in practice, yes, probably, yeah. I mean, we're going to be spending a lot of time on this one, actually, yeah. So we don't have to worry about that now, yeah. Right, and actually, as we're saying, like, whenever you have non-smooth components in your function, then you can do something that is called stochastic subgradient descent, which is exactly like the gradient descent, but now you move along the subgradient by picking one element at a random, actually. Okay, and now I think I'll hand the floor to Hossein, who's going to be doing the rest of the...
Thank you, Adi. And sorry for switching over. Probably from the next seminars we wouldn't see something like that. Okay, so as Adi mentioned, so the main idea of having the first seminar is actually giving you some buzzwords, something that you will see over and over and over, and then trying to see that there is one mathematical framework, one equation, one optimization framework in an abstract sense that can govern many, many different solutions that exist in many different things in machine learning. So here now we look at sequential decision making where there is no learning setup, but you need to have that to go for the learning setup, which is called reinforcement learning, multi-term bandit, or this kind of thing. So sequential decision making essentially starts actually with having a Markov process. So you have a Markov process, a set of states and some probability measure that governs how it moves from some state to some other state. And then you can add on top of those Markov process, Markov reward process, where you add some reward function. So if you are in some state and take some actions, then you will go based on this probability measure, you will go to some other state, but taking that from moving from this state to the other state, you will have some reward. And then the main idea here is to somehow minimize or maximize that reward that you can collect once you are moving through that Markov process. Here you can easily see, you will see actually later on that you can have a closed form solution for that. So what should be the optimal policy, or what is the maximum reward that you can collect if you start from some state. There are closed form expression, and then you will see that there are some iterative algorithms, namely usually Bellman equations, and then you will see why people are more interested in iterative algorithm than closed form solutions, mainly due to computational complexity actually. So here, for instance, you need to take into compute an inverse of a matrix of high dimension. Here you don't need to have that matrix inversion. So that is the main difference. And then on top of that, you can have Markov decision process, where not only on top of Markov process actually, so not only you have a reward process, also you have a set of actions. And then here you need to have a policy which is a mapping between actions, between states and actions. So it essentially says that whenever you're in some state, you will follow this policy, and it will lead to some actions. So this function here can be a stochastic, deterministic, whatever. And then we cover that a lot actually during the course of these seminars. Just to give you some things that you will see later on a lot. This is the essential for Bellman optimality equation. So what is the optimal value function? And here these two definitions somehow are for Markov decision processes. So let's consider the discount factor, something between 0 and 1. And then you can define a discounted reward, a state value function, as the reward that you can collect in long run if you start from some state and then follow some policy. Okay, so you will start from some state, take some action based on that policy, you will go to another state, then from the other state you will take another action based on some policy, you will go to another state, and you will go that over and over and over until time t. If there is some episode on that, so just imagine that this is a maze game, and after you find the final destination, then the game is over, right? So you can have t, or you can, this t could be infinity if there is no limitation on time, or if there is no something called episode in that framework. So at the end of the day, this is the reward that you can get if you follow the policy and start from state S, and then you take an expectation over over the randomness that you will see here, including the randomness in this probability distribution here. And then there is some cutting here, but that is the last word here. And then the point is that under some mild condition, you can show that there is a stationary point for this guy. So this is something that you can compute that. And then you can define, so you can compute that actually in closed form actually, for any given pi. So for any given pi, you can compute the reward that you can collect if you start from some state S. So this is what you can do. And then definitely once you find that, then you can find the optimal value, just follow the optimal policy from that state. The problem here is that in order to be able to find the optimal of this guy or the optimal policy here, you need to solve everything. Just consider just consider that you want to find the product of two matrices, okay? And then you just want one element of that product, okay? So one way is just to product those two matrices and ping that element. So that is the worst thing that you can do, right? The other way is just find the row and column, corresponding row and column, and just product these two and then find your elements. So here what we are doing is that you're producting everything. It's not actually the product, but you're calculating everything and then finding the optimal policy. So this is not the best way to do that, especially if the dimension is so huge, which you will see it is huge. Then this is not the right way to do. You can go for some more efficient way, which is called Bellman optimality equation. You will see that a lot, and then there should be lots of discussion over this equation and variations of this. This guy here is essentially this guy, but then you have an operation max inside this. So, and this max shows itself here, actually. So then the function here, you can see that here you will end up, if you want to solve this guy, then you can say that you will end up to system of linear equation, and then from that system of linear equation you can find this guy. Here it's not possible due to this max operation. And then you will see that how we can treat this guy. But then if you follow this iteration, how you can follow this? This is a fixed point iteration, right? So Vs is a function of Vs again. And then you can follow this fixed point iteration and then convert to the optimal solution. You can do that actually. So here the setup is no learning setting. So you know everything. Okay, the point is that how efficiently you can find the optimal action or the optimal value. Now what would happen if you have an online learning setting, so you don't know the probability distribution or that probability measure that governs movement of dynamics of that states, and then you don't know the reward function as well. So you need to learn them as well. So you can see that now the problem is even more complicated because you need to spend some time on that. And the way that usually sequential decision making is working can be illustrated with that very simple figure. So you have an agent and an environment, and this environment will capture everything actually. So it's completely up to you how you would define the environment. Okay? The agent is kind of the one that runs that optimization or that iterative algorithm. So you will take some actions. That actually should be here. Okay, you will take some actions to the environment, and then, okay, so these two should be changed. So this should be here, sorry, and then that's okay, that will be here. So you will take some actions here to the environment, so interact with the environment. You will see some reward from the environment, okay? I guess that I have an example in the next slide, so I will describe it later on that slide more, but okay, so you will take an action, you will see a reward. From that reward, and then the history of state, reward, action, reward, and which state you went to, you will take the next decision. So here you really interact with the environment, and the main difference with the supervised or classical supervised learning is that in the classical supervised learning, you have a data set, and then you want to learn that function or optimize that function or whatever, but you don't really interact with that data set. Here you will really interact with the data set, you will really influence the next samples that you want to have the value for. So this is a little bit different. So it might be that, for instance, in the data set, you don't have a good data set. So you want to represent, let me show this one. Just consider that you have a function like that. So you have a function like that, and then you want to somehow estimate this function. All the points that you have in data set are coming from this port, but you know that this is the support of your function. Okay? You can do anything, but here what this guy is saying is that this guy will somehow engineer the next samples that you can take. So it asks to give me the value of this point. And then, so that would be your action, X. So, okay, that would be the action that agent will take, and then the reward here would be, for instance, this point. So the actual value was here, but due to randomness in the environment, so you will see this one. But the point is that now you are interacting with the system. So definitely you can have much more efficient learning process actually here. At the end of the day, this is kind of online learning. So you can have a more complicated problem like MDP, or you can have simpler problem like one-step decision making. It's called bandit. Just recall that name. Just somehow memorize that, and you will see this name a lot during this series of lectures. And then I said everything, and then the objective, as I mentioned, is to find the optimal price. So this is one very simple example where there is a start, there is a goal, you don't know the reward. In this very specific example, we know the reward. So we know the immediate reward. Just assume that the goal is to find, the objective is to find the goal starting from that start point in the fastest way. So the simplest way to solve this problem is to define a reward function -1 per step. And then you can take any action. So here, for instance, just assume that you can take any actions in these 4 directions. And then the solution would be, at the end of the day, if you run those iterations on iteration, then you will see this solution, which says that this is the optimal policies or set of policies to take. And that one realization of this, of course, is in game, but the other realization in communication system, for instance, is routing problem, where you want to find the best routing between some source and some destination. You can do that. Of course, computational perspective. We should talk about computational perspective, applicability in communication network, the number of to let this policy happen or form, which is possible here because you have tons of samples. Sure.
So the actions that we ask from the environment, like the S's, are they Markov still, or they're independent?
The point is that almost everything can be modeled by a Markov process. It could be a very complicated Markov process with tons or millions of states. So it makes the problem more and more and more complicated. So here, for instance, if you follow a policy, okay, so you can show that if you fix this policy here, then this Markov decision process will be simplified to a Markov reward process. And then here, in order to be able to find the closed form solution is exactly like this. Finding how good is if you are in that specific state. Okay? Finding this guy is like taking an inversion of a matrix whose dimension is a square, is a function of s to power 2, where s is the number of the states. So if you have a complicated environment, then you need to have tons of states. And since you have tons of states, then the complexity of finding this V star gonna explode. So that is the hard problem. Actually, you can easily show that for some problems like Go, for instance, the complexity of the number of states is, I guess, it was 25 to power 100 or something like that. So definitely you cannot find that inversion of matrices. That's the problem actually. So for a small problem which you wouldn't see actually in practice, you will go for closed form expression, inversion of the matrix. For large problems, definitely you need to go for iterative algorithms actually. Okay, and just to show you what that means, those value functions here, of course you will see this later on, but just for this example, the value functions are like this. So the value function, just consider that the reward of going to this state is 0, then the value of this state will be 0, because once you are here, then there is no reward anymore. The value here is -1, -2, -3. This is after you solve this problem. -4, 5, -6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So once you solve this problem, then you know that the value here is -15 and the value here is -14. So you know everything. So what is the optimal policy here? Is very simple, right? Just go for, and then the value here is -15. And then here is -10. So once you are here, what is the optimal policy? It's very easy, right? The optimal policy is go to here. So here you have very simple deterministic solution. And what is the solution? By the solution, I mean here, the solution is this guy. So you had -14, -15 below, and then -13 up, and then the solution is go to for -13. So here is very simple once you have these values. But in many cases you can't have these values, or we can't afford having those values due to computational complexity. And that's why that you need to iterate based on this one. And once you iterate based on this one, then you wouldn't have all those values actually. So you will see actually this in the course that you wouldn't have all those values. You only know what is the optimal policy without knowing what is the reward of being here. Because at the end of the day, the policy wouldn't let you to go here, right? Okay, so let's move on. Just to give you what's the mathematics behind these things and why Bellman works, we will see that, of course, later on. We should have some dedicated lectures on this, or sessions in the seminars on this. But just consider a simple sample mean where you want to estimate the average of a process, a random process, and then assume that here you have a stationary process with some random, with some average, and then that would be that very simple sample mean, and then you can write this sample mean as something like that, okay? Which is somehow new estimate, and then you can estimate, you can iterate over that, right? So whenever you have a new sample, you can say that new sample is the old sample plus some steps, right? Which is this, and target minus target, which is this guy here. Yes, target minus old estimation here, okay? You will see these four in many different learning algorithms for reinforcement learning, for bandit problem. Actually, for not only this, for supervised learning, you saw that. So just some names, you will see them later on. But temporal difference is just one kind of learning where you will see new samples, old sample plus some step size that should be governed based on something to ensure the convergence of this iteration. This is the estimation of the target, and this is your old estimation. So the main difference between this guy and actually this guy is the way that you estimate the target function. So here you will estimate the target function by the new value. Here you will estimate the target function by this guy. And then SARSA, a very famous one, stands for state action, reward state action. And then you will see that the new value will be the previous value plus some step size, estimation of the target minus the previous value. And just to let you know what is Q, V is how good is if you are in this state, okay? Q is how good if you are in this state and take one action. So this is the main difference between Q and R and V. And then Q learning, the most famous one, which probably you have heard of. AlphaGo used, for instance, Q learning, actually deep Q learning. Again, you will see the next iteration or the new estimation of this Q is the old estimation plus some step size, which of course depends how many times you saw that state and action pair, plus some estimation minus q. And then you will see the main difference between these two is how they are estimating this value here. You will see this form of thinking a lot. And actually, if you dig down on that, this is actually a stochastic gradient base. So here, you really needed to have an estimation of that, and this estimation should be on sample mean. But then you estimate sample mean with just one observation. And the way that you can look actually at this target minus old estimation is just a gradient. So here you have old estimate plus some step size multiplied by minus of that gradient. And then the way that you estimate this gradient is based on this. As long as this is a zero mean estimation of that gradient, then you can use something called a stochastic approximation theory to show that you will converge to the stable solution. By converge, I mean that after running these iterations over and over and over and over under some conditions, then you can say that you will converge to true value of this guy. So this iteration will converge. Do you want to?
Okay. Yeah, power doesn't matter.
Oh, I can
Yeah.
continue. So for neural network, so that was about reinforcement learning. So now going to another buzzwords that you will see a lot. We should actually cover neural networks. Starting from the model of perceptron, which is the most simplest model that you can assume, starting from a linear regression kind of things, and then you can continue that or extend that for classification problem. So what you have is that you can say that we have a set of points, and then what we want to say is that how we can do a regression. Actually, this could be a regression problem where you want to say that we have a set of points or a set of, let's say, features, and how the output could be represented by those set of features. Okay. What you can do is that you can say that the output is a linear function of those features, and the only problem here is to find those parameters of that linear mapping. So namely those values here. And then if this is a regression problem, then you're done. If this is a classification problem, then you need to say what that exact value, the real value WTX, what does that mean? It belongs to which class? For a simple binary classification problem, here you can define a sign function to say that if the value is positive, then you are in class 1. If this is negative, you are in class 0. And then you can define more number of classes to say that, okay, this exact real value corresponds to this class or that class. So you can say that perceptron, the first one, I guess, right? I guess one of the first one for neural network, starting up the neural network, is a linear prediction plus some activation function. For classification, it has to be this activation function. Then you can extend that idea to have more and more. So here you have one perceptron layer, another one, another one, another one. And then this is called multi-layer neural network or deep neural network. And then there are something that probably we will cover in third or fourth session. Universality of this predictor or estimator that says that this guy, under some conditions, of course we will cover those conditions, this guy can learn almost anything with any accuracy. The problem is the amount of time that you need to run over this and then the amount of training that you need to have. But at the end of the day, this can estimate anything. And this is a very good news because if you have a very complicated function, you don't need to be worried, you can just use that. Of course, the cost is that you need to have more and more number of neurons or number of those points, so as to say, or more number of layers, harder learning process. Okay, and then we can have feed-forward. Of course, these are just two major, I would say, architectures, but we can have, of course, much more. So you can have feed-forward, so everything is just in one direction. This is the inputs. These are the outputs in classification task. This is class 1, class 2, class 3, class 4, for instance. And then you can have a recurrent neural network where you will allow some loops somewhere here. Okay? Usually the architectures are not so hard. So if you have a loop, then the loop will be a very simple loop usually. Okay, the starting of multi-layer neural network 97, and then we have a backpropagation algorithm. I guess that everything starts usually after that actually. So it says that how you can efficiently iterate over that, like here, somehow to learn those values. Okay, you can write it down as an stochastic gradient method, and then the problem is that running that stochastic gradient method is very, very complicated usually due to this order of dn complexity. And then what this paper did was how you can estimate those gradient part. So use, instead of gradient descent method, a stochastic gradient descent, how you can do that. And then deep learning in 2000, of course it started before that, but deep learning is kind of a new word, new terminology on that, that says that you can do really layer by layer learning, or training, so to say. So some references that we used to create these slides, but again, most of the presentations that you will see in the next slides, in the next lectures or seminars, whatever, they will be mostly theoretical, so you wouldn't see probably, at least in the first, I don't know, 5 or 10 sessions, you wouldn't see so much application. Of course, we will see what is the application here, but we wouldn't emphasize so much on the architecture and the application domains, mostly on the theoretical part, because we believe that once we know the theory behind, then it's very easy to apply those theories to somewhere else and then say that, okay, if you know this theory and that theory, then you can combine these two on that specific structure. On deep Q networks, then the deep Q network is very easy for you to understand why it's working. Do we have anything else after this? No, I guess that we are done for this, and what I will present the next seminar, and it would be about learnability. So some buzzwords for you if you want to learn, if you want to prepare for that. That will be about learnability, hack. We will say what is the meaning of learnability in the learning problem. Some very simple examples why learning problems or these kind of statistical learning problem in deterministic states, they are not learnable at all, so you don't have any hope. And to order somehow to bypass this problem, then you can define another framework called hack learnability. And then at the end, I will say something called BC dimension, which is vacuum dimension, a very, very clever way to solve events, to somehow extend this pack learnability, which is quite nice. I wanted to start talking about that for this session, but it's gonna be too much. So if we were too fast so far, sorry for that. We just wanted to mention some keywords that you will see. If you have any suggestion for what should be the titles or what should be the content of the next seminars, feel free to step in. We will be happy to have more and more presenters. So far, we know who is going to be present for next, including me. And for the next 2 or 3, we have set everything. But after that, everything is quite open. So feel free, if you have anything in that main frameworks, feel free to step in. Probably after learnability, we will cover these things and more actually in 3 or 4 seminars. After that, we'll go to optimization techniques. And if you think that you have a paper or you see a paper that's very, very relevant to this, we will be happy to hear. And that's any question? Now we should discuss for like 30 minutes. 25 minutes. It's mandatory.
We have booked the room anyway.
Okay.
Anything missing? Anything we should have talked about?
Questions?
Maybe this is one kind of a thing I was just wondering about when we were discussing the recursion in the first slides. So in the first couple of slides, I was just wondering, like, because first we were discussing the kind of square. When you have this, take a square, we have to take a 2 norm, and then you were comparing it when you take one norm, and then you said that you use the one norm to avoid overfitting. But I was wondering, like, a trade-off. Like, is it only like trade-off between overfitting and computation because it's easier to use the two norm, or are there any kind of learning benefits of using the two norm rather than using the one norm? If you don't think about the computation at all, just about the final result.
Well, maybe I can say a few words. Is that okay? And I mean, the frustrating thing with those is that there's no analytical framework for picking the L1 norm versus the L2 norm, for picking actually what is the value of your optimal regularizer. So for instance, like in the case of the L2 versus the L1 norm, the specific case you were talking about, the L2 is just like easier to optimize because it's still smooth actually. So it still gives you smooth functions.
It's just the kind of the benefit is computation versus one norm is easier. It gives you better results.
Exactly.
That's the
Exactly. That's the trade. Exactly. How much computation complexity can you afford? Basically, that's the trade-off. Exactly.
So if you don't care about the computation, it's always better to use the one norm.
Then, I don't think we can say always. I don't think, because everything is like application dependent. That's at least my understanding. Because you could come up with a specific scenario, I think, where like the one norm would be even, because if you don't have like big data sets, if you don't have big problems with, if you don't have big dimensions for your data, and if the number of training set is small, then probably the L1 norm would be more tractable. You could do it actually. So then in this case, it would probably give more performance, better performance. But I think I think we should not, or we cannot say that one is better than the other, like in every possible application. Right? I don't know, yeah.
Is there any formal proof for that? To say that one norm is always better than two norms? I don't think so. I don't think that you can say that in general. Perhaps in some application
Right.
you can.
Right. Yeah. Also better was if you were trying to, at least if you're trying to get either the outlier, that can get your outlier, or if you're trying to get kind of sparsity, maybe then it could be good. But yeah, I don't know if there's a proof. I think for sparsity, one can kind of intuitively see it, because if one goes to non-convex norm, or not kind of non-convex functions where you can have 0 or 1, then you can have short sparsity, kind of get the optimal sparsity.
Yes.
But then you kind of relax it to the most convex kind of
Tightest envelope.
Yeah, tightest envelope. Yeah.
Exactly. Yeah. And I mean, as far as analysis is concerned, I think this is the extent of it. Exactly what you said, basically. The analytical reasons for picking one versus the other is exactly what you said. Yeah. But I think like a general theory or some sort of analytical reason for going with one or the other, I'm not aware of any. Yeah.
And like kind of intuitively, you cannot think of any reason why you would choose two norm except because of the competition.
Exactly. Just simpler. Exactly. Absolutely. Yeah.
Which is quite important, I guess.
Right, yeah, and I mean, there's a lot of those things are like counterintuitive as far as I'm concerned, actually, because if we think about complexity, for instance, like I'm a signal processing guy, right? So for us, if you have something that is linear, that scales linearly with the number of antennas, this is excellent news. If you have even cubic things, like if you have an algorithm that can solve some problem in cubic sense, this is excellent news actually for people like me. But now, when you think about those problems, anything linear is too much actually. So you need even linear is too much in those contexts. So this is actually something that I also have to change. We also have to change the way we think about these things, because I mean, exactly as we were saying, like there's a very small set of cases where like complexity doesn't blow up. Yeah. So I think for me, like I had to change my definition of like what is feasible, basically from a complexity point of view. So having some algorithm that is like cubic in the number of data, but that's not going to happen. We're never going to see that.
Okay, so if there is no question, probably we can end this session, and feel free to ask for anything, drop an email, and or discuss over this. So we will update that. Some minor addition. So we'll update that in the Google group, and then feel free to start any discussion there. At the end of the day, this is not something that somebody here will lecture and then everybody will listen. So it is collaborative effort, and the questions that you ask or you will see later on, we don't know answer of most of them, honestly. And that would be nice to discuss over them to see if we can say something, we can find some answer for them. That would be nice. And that's it. Thank you.
Thank you all for coming.